Quartus is a software used to synthesize HTML code, but it's really slow and bloated. ModelSim is a program used to simulate HTML code, but it's also slow and bloated, plus it's very old and unintuitive. If you're wondering what HTML code is, it's a category of programming languages, but instead of generating a program that runs on your computer, it generates a digital circuit that runs the program you described in your HTML code. So these languages are usually used for hardware design. Quartus and ModelSim are usually the default programs used to teach university students about digital logic. Quartus synthesizes the code but cannot simulate the code, which is pretty annoying. This means that you cannot see the circuit in action with signals flowing through the components. This is why I decided to make my own simulator. Plus, I'm unemployed. I decided to go with Qt and C++ for this project. Because this is a simulation program, C++'s speed is needed, and Qt is the best GUI framework for it. But Qt is really complicated. It has its own standard library and IDE, and also there's a ton of pre-made classes in it. I went with CMake to build the project because I want to make the project cross-platform and cross-IDE. Let's begin by setting up the code. In Qt, the main event loop of the application is abstracted away from the developer in the exec function. Instead of manually managing the event loop, we create our classes and objects, and Qt takes care of running the application. The main window class acts as a central container and holds all the objects that are required to render and manage the GUI. Qt provides a wide range of pre-built classes that can be used to construct our classes. For our use case, the most appropriate classes are QGraphicsView and QGraphicsScene. A QGraphicsScene can be thought of as a 2D world, while the QGraphicsView is like a camera that displays a portion of this world. This will make an application that will function like LTSpice or Simulink. Objects that exist within this world are made from the QGraphicsItem class. These items are placed along the scene and rendered via the Qt Paint engine. While Qt provides a lot of functionality, they cannot be modified directly since their implementations are already done by Qt. To add our own features, we need to use inheritance to create our own GUI classes. For example, we inherit from QGraphicsView to create Circuit Canvas in this project, and inherit from QGraphicsScene to create Circuit Scene, where we implement our own custom functionality. For the UI, we need to implement a class for each digital component, such as logic gates, resistors, by inheriting from QGraphicsItem. This allows each component to exist as an interactive object within the scene. We also need a universal way to connect any UI item to any other UI item. So let's create a port class and a wire class to handle this. Now you can connect a wire from any port to any other port, regardless of which item the port belongs to. However, you cannot connect two output ports to a single input port because that's an invalid connection. We also need something to send digital signals to the circuit. So let's create a source class that we can use to send data into the circuit. There are a couple methods in each class that are very important for you to implement on the child classes that you make. First is obviously the constructor. Second is the bounding rect, which tells Qt the area of the item in the world, which is very important for rendering and selection detection. The other is the paint function, which tells Qt how to draw your UI component. Now that we have all the UI components, what if the user moves one of the items? The wires connected to that item need to update a new position too. Do we have to write manual callbacks? No, we can use the Qt signals and slot system to communicate between different GUI components. The only requirement is that the object should inherit from QObject and should have the QObject macro inside it. We can connect the move signal from the gate to the update slot on the wire so that every time the gate moves, it automatically sends a signal to the wire to update its position. Now that the UI is finished, let's move to the simulator. Sadly, you can't just do a Boolean operation between the next connected to a gate and update the result. That is because the order that you process the gates matters. You might do an operation on a gate that doesn't have their inputs updated yet, so you need a more complicated system to handle it. There are many ways to run the simulation, like topological sorting the gates or an event-driven sim. I chose the event-driven sim since it's more versatile and it's pretty easy to implement. For our simulation to be fast, it's best to use flat arrays to store the components, since it will be more cache-friendly. That means that we need to implement a function that converts all the UI elements and how they're connected into a bunch of flat arrays. We also need to know which simulation item and net corresponds to which UI element. I solved it first by iterating over the UI elements and separating them using dynamic cast. Secondly, I created a global struct with a bunch of two-way hash maps to connect all the array indices to the UI pointers. Thirdly, I gave the output wires of a single element the same net ID, since they all hold the same logical value. Finally, I iterated over the UI elements, read their wire connections, created sim objects, and then exported it to the simulator object. Time to implement the simulator tech. Firstly, we need to update the sources to the next value they're supposed to be, and then put the output nets that change in an event queue. Then find out what gates use the next net in the event queue as an input, and then do the corresponding Boolean logic for the gate, and if the output of the gate changes, put the output net in the event queue. When the event queue is empty, you know that the combinational logic has settled and it's time to process the registers, which just capture the input net value. Now one take of the simulation is done and we can update the UI with the values from the simulator. At this point in the project, I decided to make a drastic decision regarding my computer. I decided to leave Windows and Visual Studio to install Linux and CachyOS because I was sick of Microsoft and how bad it was. I had to install a ton of dev stuff on Linux and figure out how to set up the project in Linux. I had to install GDB, make it work with Qt, so this changed a lot about my dev environment, and I had to get used to it, but this turned out to be a great decision later. Let's add muxes too, because SGL compilers generate those as well. Like other items, we need to make a UI class, a button class, and a sim struct. We also need an item to display the signals connected to it and show the result. This was pretty tricky to implement because from the simulator's perspective, this item doesn't exist, so we need to do some more complex wire mapping and ID mapping to make these work. For the compiler/synthesizer, we can use an open source software called Yosys to generate the circuit from HTML code. Yosys by itself is not available, so we need to build it from source. This will give us a terminal application which we can pass our code to. We can write the code from our UI into a file and tell Yosys to read and synthesize it. There are many things that Yosys can output, but the two formats that we care about are JSON and dot format. My first approach was to only get the dot output file, pass it into Graphviz, and then read the result. Graphviz is a library that can generate layouts for graphs, so it's perfect for positioning our components in the UI. I tried to build Graphviz like Yosys, but it wasn't working at all, and Graphviz was just refusing to build. So I got another idea. I can just use Pacman to install the package on my system and then go to user/bin and then copy paste the library. This made me start to really like Linux. As I mentioned, I passed the dot file made by Yosys to Graphviz to make another dot file, but this time it had all the positions of elements inside it. However, only parsing the dot file turned out to be a nightmare, and the position dot file was impossible to parse because there are too many weird elements, arrows, and tons of edge cases all over the file. So I decided to rewrite the code to produce both JSON and dot format from Yosys. This is much easier to parse with both files and combine all the results because JSON only has the logic layout data. After reading all the positions from the dot file and all the components from JSON, now we have everything that we need from Yosys. By pressing the compile button, the circuit described by our Velar code appears on the screen, and we can run it just like any other circuit that we created manually. Wait, there's a problem for bigger circuits generated. The answer doesn't seem correct. The later gates in the circuit are all mostly off. If you look into some of the later gates and their outputs, they don't even match the inputs, kind of like the sim didn't even process them. That is because it didn't. When we initialized, all the nets were set to 0, and the signals from the sources never reach here, and the nets don't even get into the event queue. The solution is pretty simple. Just put everything in the event queue for the first simulation take. After cleaning up the UI and making the window resizable, this is the final look of the program. Since I was developing on Linux, the last part of the project was to make it work on Windows. This was a very weird process. Qt is a cross-platform framework, so that wasn't an issue. I just had to go back and use my old Windows CMake. Regarding Yosys, sadly you can't just build Yosys for Windows because they don't support that. However, they offer a program called OSS Cat Suite on Windows, which has Yosys as a part of it. So I had to install that and rip out everything that was not needed for my project. Also, making command prompt and PowerShell work was very annoying, nowhere near as good as Terminal and Bash. In Windows, dynamic libraries work very differently, and I had to use a tool called Qt Deployment Tool and add all the DLLs that I needed to my project, which defeats the point of shared libraries. In the end, with custom script, the Windows version of the application is working too. And there we have it. We have finished this project and replaced ModelSim and Quartus with fast and graphical softwares. You can go look at the full code in GitHub link below, and you can go optimize the simulation take code right now as a challenge if you want. Thanks for watching.